And so Nick, to your question that you had asked, I was incorrect in that email because we were going to go over it again today.
Gotcha.
Sorry. Okay. So we have an RLC filter, right? R, L, and C. And I'm going to label the nodes 1, 2, and 3. And there's a Python program that you'll learn in lab that if I tell it I want a low pass filter, second order, and then there's something called Butterworth. Now, what Butterworth means comes later, but that really means there's poles and they're complex and they're evenly spread on a circle, okay? And that has some interesting things we like to have in a filter, right? So if you tell it low pass, second order Butterworth, it's going to give you some constants. All right. It doesn't print it out nicely, but it's going to give you a transfer function. All right. And so it gives you this constant. It gives this constant, but it's always 1, right? Oh, and then there's an S, and then there's no, oops. Now, we can tell that this is a low pass filter because if I just set S equal to 0, these drop out, and then these cancel and it's 1. And then when the frequency increases, it drives this down. So it's a low pass filter. It just happens to be second order. And if I did it in pole 0 format, I would have complex poles. But this format, you know, has some advantages, all right? Now, let's derive this, you know, V3 over V1, right? It's just voltage division, ZC, ZR plus ZL plus ZC, right? 1 over SC. All right. Now, we are running a little bit behind, so I'm not going to go through all the algebra, but once you get it into the proper format, okay. All right, and this is the proper format, all right. Now, sometimes on the exam, people put the transfer equation kind of in this other format that some people like to do for the Bode plot. And, but that form, all right, I'll put it this way. If it was correct, it was correct, and I might have said, try not to use that in the future. But many times, it just wasn't correct, or because people follow this certain video, right? Low pass filters are this, but there's this video that makes you think, I mean, high pass, that it's this. But this is just like a special case in that video. There isn't always a flat spot, okay? I try to mention it, but sometimes I don't know if there's what I can do, all right? But again, you can, we can make that up on the midterm. All right, so now here are my design equations, right? And A1 equals R over L, and A2 equals 1 over LC. And you might realize that I have 2 equations and 3 unknowns, right? So there isn't just one solution that's going to work, right? And as I mentioned last time, right? Choose L, Calc C, Calc R, evaluate the design, right? Is R greater than 2K? And that's just, all right. Now, I think I'll post these notes, but the reason why R has to be greater than 2K is you want this whole impedance to be bigger than whatever impedance is inside the voltmeter. But the impedance of the L and the C are changing. And what happens is at omega naught, the impedance due to the inductor cancels out the impedance due to the capacitor, right? If we look over here, right, at omega naught, these two equal each other, right? And so the minimum impedance, right, is when these cancel each other out. Now, it's a rather long derivation. If you're interested, I can send it to you. But I wanted to get to more examples. All right. So let's try it. All right. L equals 10 microhenries. Okay. So then C, when I do the calculations, will be 1.1 microfarad. All right, I can buy those. There's something very close, right? But when I calculate R, I get 4 ohms. And so, you know, if I have 50 ohms impedance coming out of the voltage source, right, and I have an R and an L and a C, right, at omega naught, these two impedances are canceling each other out, and that voltage division between 50 and 4 is going to really attenuate the signal. It's just not going to work, all right? Now, I could go the other way and try to find out what inductor do I need. All right, so the minimum, if I put R minimum, right, that's 2K. That's the smallest it can be. It's not a hard and set value. It's just that's as small as I want. Divide that by A1. All right. I get 4.4 millihenries. And if I look on the Anchor Electronics website, the closest match, right, is 5.6 millihenries. It's got to be bigger, because if it's smaller, then it won't be R min, right? Now I calculate C, and I get 1.8 nanofarad. Then I calculate R, and I get 2.448 kilo ohms. Now, we know that we have a limited range, right? So you can get 2.49 kilo ohms, and right? And so that would be your design. And then you could put it in LT Spice and then simulate it. And then what would be great about LT Spice is, well, if you can vary these parameters, right? Because nothing, when you buy it, right, there's a variance, there's a tolerance to the parts. And you could see, I could kind of do a Bodie plot, like this is the magnitude if everything is exactly what it's supposed to be. But if, there'll be a higher magnet, there'll be things shifted one way and then shifted the other way. And I'm exaggerating a little bit based on the tolerance. Hey, I'm sorry. What does caret mean?
Usually means when someone puts it under a text, it means they're just repeating the same thing.
Oh, okay, thanks. Sorry, sorry for my ignorance. Okay,
That's fine.
all right, Sam. So I'll answer your question. So what, right, if we looked at that equation, right, we have A1 equals, I believe it was R over L. A2 equals 1 over LC, right? I only know two things, so I can't do anything. But actually, I do know something else. I know smallest R, right, is 2 kilo ohms. Now, how do I know that? Is I've read a lot of, I keep talking about this 50 ohms, right? But what's usually is this voltage supply or voltage source is an op amp. And almost every op amp I've seen, it'll say the smallest resistance you can drive is 2 kilo ohms. So it doesn't have, it's not exactly 2 kilo ohms, it just has to be bigger. So then that gives me a range for L, right? L has to be bigger than this value, right? And then I go and back calculate everything else. Does that help?
So for A1, would you use R minimum?
It doesn't help. Yeah, 4.4 is the minimum value of the inductor, right? I mean, I could say L has to be bigger than this value, right? Maybe that helps. Okay, Sam, let me try maybe just slightly different approach. All right. So one thing I know before I start is that R has to be greater than 2 kilo ohms. And I'll never say the word always, but it's a good assumption in this class because in general, you can always assume some op amp is the source. And the data sheets will tell you the minimum resistance. Now, some op amps can drive smaller resistances. So you need to look at the data sheet, all right? But in the ADLM kits and all the testing kits, there's always this 50 ohm resistance. So if you make it bigger than 2 kilo ohms, that voltage division is negligible, right? And even if I want to have a tau, right, if this is my voltage supply, tau is 50 plus this 2K here, right? Where ideally it would be 2K combined with the resistor. But 2K plus 50, the difference between 2K plus 50 and 2K is negligible, right? But I just tend to use 2K. It's a good starting place, all right? But, you know, in real design, you can't just say always, all right? Maybe you could say mostly, all right? And when I say in this class, I'm meaning, you know, in this class, we use signal manipulating op amps, which tend to have a 2K minimum resistance, okay? So anyway, back to here. That's the minimum, right? So if I have A1, right, and then I have this R that's greater than 2 kilo ohms, right, divided by L, right, then I can have this solve for L, but it's not an exact value. It's just, you know, for R greater than 2K, right, divided by A1. Well, for this to be true, then L has to be greater than that, all right? I'm going to have to leave it there for now. Okay. Oh, and those office hours, right? They can be for anything, really. It's not just about talking about the exam. Okay. Oops. Right. So H of S equaled, and those constants came from a program for a 50 kilohertz filter, right? So if you want a different filter characteristics, you would just change the program and it would give you different constants. All right. Yeah. All right. Anyway, you know, Sam, I'm glad you kept asking your question, right? Because I bet other people had it too. And thank you, everybody, for answering the question. So let's just derive this out. And V2, V1, no, V3, excuse me, V1. I've changed the position of the inductor, right? It's going to be ZL, ZR plus ZC plus ZL. All right. So I need to get it in. Now this isn't a good format because it has the, you know, S is a raised to the 1. But here I have this 1 over S. So I have to get it into something with S squared, something S, and something without S. So the only way to really do that is to multiply through by S. That changes the numerator, right? And I get SR. And yeah, I'm going to start moving things around. All right. And now it's really much better to have this scaled by 1. The way I'll do that is I will pull out an L. Now, this is super important, is notice, oops, the denominator is the same. S squared, S times R divided by L, 1 over LC. But the numerator is now S squared. So when I set S equal to 0, right, no, not, if you look at the, if you were to do this in pole 0 format, right, and S were headed towards 0, right, you'd have 1 for, well, actually, if I set S equal to 0, this is 0, and then as S heads towards infinity, right, these cancel out and it flattens out. So it's a high pass. Okay. Now, yeah, Bode plots never go to 0, right? But so it's a high pass. And alls I did was move this around. Now, the thing is I really, if I had a circuit and I wanted whatever was coming across the resistor, right, I could put, and I'm sorry, let's put that at a plus and let's put that minus. I'm not going to draw it. I could put a differentiator circuit that will find the difference across these 2 nodes, and I don't actually have to take it here, right? And so VL gives high, VC gives low, and VR gives, and we'll go into band later. Now, here's something else I mentioned last time. VL plus VC equals notch. Okay. So now I need to design this filter. Well, really, let's say 50 kilohertz. Oops. Right, Butterworth. Second order. It's all the same, right? the R, L, and C values we calculated in the previous example will make this here into a high pass filter at 50 kilohertz. And I'm just changing the definition of V out, right? And if I wanted the band pass, right, I could just, I guess here's the thing. Normally when we're doing the voltage divisions, right, we always take this last one and kind of put it on top. But if I wanted the voltage division of this whole stack for here, I could just write it directly. And then manipulate everything. But the denominator is the same because it's all the same circuit, right? The current is in series and it's all the same. Okay. Now, what I found is that for that 5.6 millihenry inductor, for this configuration and the constraint of R min, that 50 kilohertz is about as small as I can go. And if I want to go below that, it won't work. I can't find an inductor that's big enough. Now, if you can find inductors that are bigger, but let's just say for inductors can get big and expensive. So you always want to have more than one way to do a filter, right? But the reason why we can get complex poles is we have two different kinds of storage and energy storage. One stores charge, right? And one stores what? The movement of charge, right? Potential energy versus kinetic energy. Now, in the book, there's something called DF2 and DF1, all right? And the book, right, has a second half to it, which is more like EE112 material. And so DF1 is really for what you might call DSP systems or filters. And there's reasons why that I'm not going to get into. So it's a valid technique, but in 110, it uses too many op amps. So I don't cover it. I don't use it, right? But DF2 is actually a kind of derived from DF1 where it shares op amps. But in looking through a lot of EE110 like textbooks, they never mention this. In fact, even like a Google search doesn't come up much with DF1, it's called something else. And DF2, even though it acts on the transfer function, right, a better search term would be state space filter. And you can independently tune any parameter you like, and you can make it as many the order you like. All right. And so there is there's the way to derive this filter, but then the way that you actually create the filter is a lot simpler. All right. But what I'm going to do is just draw at first a generic architecture of the DF2 design. Okay. It starts off with a summer. All right. And I'm just gonna, it's a function of S. I'm just not gonna draw it, all right? And then it goes through a gain stage called B naught, and it goes to another summer. And there's our output. And what this, if I just drew this, right, what's YS? Well, there's only one thing coming into it, B naught, which is only one thing coming into the summer. So really it's going to be X times B naught, all right? But the state space filter design, actually, it starts off with an integrator, right? Because if I just did this, right, you know, Y equals B naught X, well, you don't need anything fancy, right? All right, that's just a gain stage, right? But now we're using the feedback method that we talked about last time. Yeah, so Clifford, I don't know of anything MATLAB can do that Python or some Python library can't. And I don't know of anything Python can do that MATLAB can't do eventually, okay? And other tools out there are Mathematica, Sage, and things like that, right? And 112 uses MATLAB, right? So some faculty use Python, some use MATLAB, all right? So we have 1 over S, and that's fed into a gain stage, and then it's put into a summer, right? And then we can have another integrator, and that would be fed in here. And then we have another integrator, and that would be A3, okay? So these are the feedback loops, right? But then we also have what you might call feed forward. Okay. Now, this is a generic equation. And just let me write this one thing and then I'll look at the chat box, right? This is going to be B0, no. S squared, S cubed. So this would be if every term is here, all right? But in the previous example, right, we really just had HS equals, we called it B2 S squared plus A1 S plus A2, right? So that this is the generic thing, right? There's only B2 is here, right? So the signal would come out through B2, but there's no B1, so you get rid of it. There's no B0, so you get rid of it. There's no B3, so you get rid of it. In fact, there's no A3 either. So if there's not a need of either one of these, you don't need that integrator, right? Now, here's the thing about the A constants. You need them all, right? Unless you're making some unstable system, all right? So you need that, you need that. And so, well, why do you need a summer if you're only putting in one thing, right? So this would be a generic outlook or a generic thing, which then you would delete things off of depending on the transfer function. Sorry about that. I miscounted. Now, this was the transfer equation we used in the RLC example, right, where I have S's. I don't have 1 over S's, right, because you can see that this is 1 over S times 1 over S, so you get 1 over S squared, and then you feed it back, and then you feed it here. So where are these kind of integrators coming from when it doesn't look like there's an integrator in the transfer function? And what you do to see that it's there, right? And now I'm just going to continue with that other example. All right. How do I see it? Well, actually, you multiply by the integrators. So if it's S squared is the highest order in the denominator, right? Multiply through by everything by 1 over S squared, right? So now I get B2 divided by S squared. I get 1 plus A1 divided by S, and then I get A2 divided by S squared. Now, the denominator is how you kind of build the signal flow graph from here, where you just have a summer, right? And that first constant, there's no integrator. It just comes right out of the summer, right? Then I have 1 over S, right? That's the S. But then I scale it by A1. Now, why, if it's positive, right, is it actually negative feedback? I kind of went over that last time. I can go over it again in office hours if you like, okay? But I'd like to finish some examples, right? So that gives me this part. Then I need to get another integrator.
That's a quick question.
Yep, just let me finish this drawing. Right. Now, notice B2, it's being divided by S squared. So in fact, S times 1 over S is 1 over S squared. So that's out. What's your question?
So is this for homework number 8?
No, it's for 7.
Because the homework is this Sunday.
Well, that can't be right then. Okay. What I do is I go a few ahead of time, right, and fix those due dates. All right. But 8 should be gain bandwidth. Okay. But really that. Okay. So now the next part is converting this into a circuit. All right. Now summers, you know, and actually integrators, you know, right? So summers, you know, look like this, and integrators look like this, except it's 1 over RCS, right? And so if, like I can skip a lot of steps by just looking at it, oh, it's S squared, that means I'm going to need 2 integrators. And it's going to be these just chained together, right? Because as the signal goes through here, that's a series type signal flow graph, right? This is a feedback type graph. And then these are actually summing or almost like a parallel, right? So this technique uses the series and it uses things in parallel and it uses feedback. So I know I need 2 integrators, so I just draw it straight out like that. Then I draw my op amps in between and tie everything nice to ground, the way it's supposed to be, right? And all right. So we'll call that R1 and C1, right? And so what's coming out of here? Minus 1 over R1 C1 S. It's already inverting. So when I sum it, I don't wish to make a minus sign, all right? Now here, what's coming out of here is plus 1 over R1 C1 R2 C2 S squared. It's already positive. Negative. We use negative feedback for these things, so I have to put it on the inverting side. Okay, and that's R A2. Now, if I set A1 equal to 1 over R1 C1, and then set A2 to I have to double check. All right. I have an example I'm going to go over more specifically. But basically, I can make A1 by selecting these here. Then A1 is being fed in. So I have to do R2, C2 to make sure that I'm getting A2 already. Then I just have to worry, I'm not putting any gain. It's just, you know, in isn't being scaled, so that's a gain of +1. And in this methodology, I'm not multiplying this by anything else. I just want it to be a +1 gain. So I have 2 here, right? I have another one coming on here. I need to balance it. And there's my RD. And I can set all of these equal to 100K, right? And that's C1 and C2, I can make a microfarad or a nanofarad. And then R1s and R2s will be the things that I'm going to change. Now, let's do a 4th order low pass filter. And this comes from the same program. You just tell it the cutoff frequency, which is supposed to be 10 kilohertz. You tell it 4th order, and then you tell it the Butterworth style, and these constants come out. And I look at this and I see it's just like before, right? I can modify everything. Let's see if I can do this without rewriting it. S4 is the highest order. So I divide that by 1 over S4, 1 over S to the 4th, right? So this becomes, excuse me, 1, this becomes A1 divided by 1 over S. This becomes A2, 1 over S squared. This is A3, S cubed. And this is A4, S to the 4th. All right. So I know that the numerator is where I'm taking the output from, and I have to take it out of 4 after 4 integrators. All right. And that A1, this is my constant that gets fed back in after 1 integrator. This is my constant that gets fed back in after 2, after 3, after 4. All right. So now the thing is as time goes on, right, you don't even do this part. You just know that as long as everything is in decreasing polynomial order, right, that's going to be the first integrator, second integrator, right? So we need 4 integrators. So I'm going to draw those first, right? All right. And I'm not the world's greatest artist, but notice I'm kind of doing it in this very regulated, organized fashion, because this technique is an algorithm, really. Okay. And you want to make sure that on the exam, you're drawing your schematic correctly. So while my open math might be able to deliver this, there's no way you can draw a schematic into my open math. All right. So anyway, there's our 4 integrators. The output is only coming out of 1 node, right? And it's going to come out of 4 integrators. And so I don't need an extra summer. And I have a lot of videos and examples that show you when and where to add that summer. Oops. So then I'm just drawing my generic summer. Here's my in. I know I'm taking out here. And I also know that this will be minus an integrator, then positive an integrator squared, minus an integrator cubed, and then positive an integrator, to the 4th. So I don't need to invert this, right? Because it's got an even number, all right? Here's this is going to give me a minus. I want to keep it minus because it's negative feedback, and I can just call it RA1. This is going to give me a positive number because it's 2 inverting integrators. It's negative feedback. I need to do that. Same thing here. And then same thing here. Now, assuming, right, that this is going to be A1 coming out of here, I'm going to choose these resistances so that that's A2. I'm going to choose these resistance and capacitors so that's A3, and choose that so that it's A4. I can just make everything 100K. Right.
Professor?
Oh, just let me finish my thought, right?
Okay.
And then I'll answer. So anyway, what's on the positive? 1, 2, 3 gains of 1, What's on the negative? 1, 1, 2. Yeah, 1, 2. And then that means I need the dummy, which I already did. What is your question?
Yes. So, can you explain again why do you have the certain integrators going to the positive feedback and then some of the other ones going to the towards the negative feedback? Am I making any sense?
No, you're making total sense. And it's one of those things, I've said the words, but this gives people the most difficulty. And the things in the denominator for this technique are all negative feedback. So when you're actually building it, and so actually I just want to finish something and then I think I'll answer that and maybe we can end here for today. Is that I do have examples that give you R's and C's and LT Spice files, and you can see how I did notches, low pass, high pass, odd number of stages, even number of stages. And we spend more than one day on this, all right? So if you're really wanting to see numbers, I do have examples that you can download right now. But this thing of why is it going one way? You know, is he just making it up as he goes along? Is it because it's pretty? But the thing is I'm going to do a quick example here. Sorry, that's a real funny joke. Right, it's time for 112. However, I am recording this, so if you gotta go, and yeah, Murad, try to keep up, okay, buddy? About the homework. No, yeah. So if the midterm is in 15 minutes and you gotta bow out, bow out. But I'll just finish this thought, okay? And then you can come hear it, okay? At your leisure. All right. Good luck on your 112 midterm. Not that you need it. I'm sure you're all going to do pretty well. All right. So I'm going to ignore chat for a bit. So let's derive V out from this signal flow graph. So here's V in. It comes in. It goes through an integrator. Oops. So V out equals V in. Goes through an integrator. Goes through another integrator. Right? There we go. But V out also depends on V out. All right. So I have V out, and I'm leaving the sign blank for right now. I come around. Oh, it's being subtracted. And then it goes through an integrator, goes through an integrator, and I'm just going to put S squared. Right? But V out, also has this loop too. Okay. So right here, this is as far as we need to go. These minus signs, right, when I start solving for V out over V in, become positive, right? And I'm going to get this kind of 1 over S squared, 1 plus 1 over S plus 1 over S squared, right, and putting it in the right format. Then if I multiply through, right, I can convert this back to the transfer function format. But every one of these in this, all the denominators, all have to be negative because we're doing negative feedback, right? Now, why is it some things positive and some things negative, right? Well, this integrator is minus 1 over R1 C1S. And then I feed it into another integrator. Which is minus 1 over R2 C2S, right? But when I multiply it together, right, it's positive R1, R2, C1, C2, S squared. But here it's all negative feedback. So on that summer, I need to actually add it back in on the negative side, where this is already inverted. I just add it in on the positive side. And so it's really just, you know, a minus times a minus and minus times a plus. That's really all we're doing. Okay. All right, I guess 17 of you didn't need to take the midterm. Okay. Let me answer whatever chats and then you guys can go. All right, Rudy, take care. And Carolyn, nice to see you. Carlos, Emmanuel, Gerardo, Hung, Murad. Oh, hey, Michael, and Larry, and Matthew. Sorry if I missed anybody. All right, have a good day.